Introduction to quantum computers. Quantum computers are a new type of computer that leverage the principles of quantum mechanics, which is the theory of how tiny particles, like atoms and photons, behave. While traditional computers use bits as the smallest unit of data, which can be either 0 or 1, quantum computers use quantum bits or qubits, which can exist in a state of 0, 1, or both at the same time due to a phenomenon called superposition. Key concepts of quantum computing: qubits. In classical computing, bits are either 0 or 1. In quantum computing, qubits can exist in multiple states simultaneously. This is because they can be in a superposition of states. Imagine it like a spinning coin. It's not just heads or tails, but both at once, until you observe it. A qubit can represent more complex data due to superposition, and this allows quantum computers to perform many calculations in parallel. 2. Superposition. Superposition refers to a qubit's ability to be in a combination of both 0 and 1 states at the same time. This increases the computational power exponentially. When you measure a qubit, it collapses into one of the two states, but until that happens, it can hold multiple possibilities. 3. Entanglement. Entanglement is another quantum phenomenon where two or more qubits become linked together. This means the state of one qubit can depend on the state of another, even if they are far apart. If you change one qubit, the other qubit's state will instantly change, no matter the distance. Entanglement allows quantum computers to process and share information in ways that classical computers can't. 4. Quantum interference. Quantum interference refers to the ability to manipulate the probabilities of different outcomes by interfering with the wave-like properties of qubits. This is crucial for steering the system toward the correct answer. How quantum computers work. 1. Initialization. A quantum computer begins by preparing qubits in a known state, often the state 0, representing a 0. 2. Quantum gates. Just as classical computers use logical gates, and, or, not, to process bits, quantum computers use quantum gates to manipulate qubits. These gates, like Hadamard, CNOT, and PolyX, perform operations that affect qubit states, causing them to be in superpositions or entangled with other qubits. 3. Superposition and parallelism. Once the qubits are manipulated using quantum gates, they enter a superposition, representing multiple possibilities simultaneously. Because of this, quantum computers can process vast amounts of data at once. 4. Measurement. After quantum operations are applied, the qubits are measured. This collapses the superposition into one of the possible outcomes, either 0 or 1, and this result can be used to solve a problem or computation. Potential and challenges. Speed. Quantum computers have the potential to solve certain problems much faster than classical computers. This is especially true for problems like factoring large numbers, important for cryptography, simulating quantum physics, or optimizing complex systems. Applications. Quantum computing can revolutionize fields like cryptography, drug discovery, artificial intelligence, and materials science. For example, quantum simulations could be used to model complex molecules in drug development, offering faster and more accurate results. Challenges. Decoherence. Quantum systems are highly sensitive to their environment. The interference of noise can cause a qubit state to collapse before it can be measured correctly, making error correction a key challenge. Scalability. Building a large-scale quantum computer is still a major technical hurdle. As qubits increase in number, maintaining coherence and preventing errors becomes harder. Challenges. Hardware. Quantum computing hardware is still in early development, with various approaches being explored, including trapped ions, superconducting qubits, and topological qubits. Summary: quantum computers are powerful machines that use the strange properties of quantum mechanics to process information in a fundamentally different way than classical computers. By leveraging qubits, superposition, entanglement, and interference, they have the potential to solve certain complex problems far faster than traditional computers. However, there are still significant technical challenges to making practical, large-scale quantum computing a reality.